Hi, thanks for tuning into the talk. I'm Sumegha and I'll be talking about memory sample lower bounds for distinguishing distributions and applications to proving security of Goldreich's local PRG in the streaming model against memory bounded adversaries. This is joint work with Pravesh at CMU and Ran at Princeton. We start with the generator proposed by Goldreich in 2000. This construction is a candidate construction for a local pseudorandom generator, and we do not know the security of this uh, generator yet, but we know the security under some restricted classes of attacks. So G takes in an n-bit input and outputs an m-bit string. It fixes a predicate P which takes in k bits and outputs a bit. It also fixes m subsets S1 to Sm of 1 to n of size k. X, which is an n-bit, x is an n-bit string, then x subscript Si is the projection of x to the coordinates of Si, which would be a k-bit string. So what G does is G takes this n-bit string and outputs an m-bit string such that each output bit is a projection of is the output of P on the projection of X onto one of these subsets. Such a construction is called a local PRG because each output bit only depends on a very few bits of the input string. Very informally, a pseudorandom generator is a pseudorandom generator is such that the output of this generator is output of the generator cannot be distinguished from a random n-bit string under limited resources. Note that under this construction, the output can at most be m can at most be n to the k because this is the total number of k size subsets. There have been many works evidencing the security of Goldreich's local pseudorandom generator against restricted classes of attacks. Recent line of work studies the attacks that are possible using SDBs. These papers identify t-resiliency of P as a necessary condition for the security when m is n to the order t. In these papers, SIs are random subsets of 1 to n of size k. This property would also be crucial to get our results and proving the security of Goldreich's PRG against memory bounded adversaries. So, in the streaming model, a predicate P that takes k bits to 0, 1 is a t-resilient if P has 0 correlation with every parity function on at most t minus 1 bits. Here, a parity function indexed by alpha, which is an n-bit string, takes another n-bit string x and outputs summation I alpha I xi mod 2, which is a 1-bit output. More formally, for all alpha such that alpha is at most t minus 1 has at most t minus 1 ones, then the following is true. If you sum over all the 2 to the k bit strings, minus 1 to the px times minus 1 to the inner product of alpha and x is 0. We also identify t-resiliency as sufficient for proving security of Goldreich's local pseudorandom generator against memory bounded attacks in the streaming model. Now let's elaborate our model on our model. We prove security of Goldreich's local pseudorandom generator against memory bounded adversaries in the streaming model, where the model is as follows. The predicate P is fixed. X is chosen uniformly from 0, 1 to n and is unknown to the adversary. This is considered as the seed to the generator. A memory bounded adversary either sees output of G in a stream or a random m-bit string in a stream. More on that. At each step I of the stream, Si is randomly chosen ordered subset of size k of 1 to n, and the distinguished sees either a stream of Si, the output of P on x on the projection of x on Si, or Si, Bi, where Bi is chosen uniformly from 0 to 1. So in the first case, of when the distinguisher is seeing a stream of Si, P x Si, then this is this is considered to be the output being generated using the pseudorandom generator G, and in the second case where it is seeing Si comma Bi, this is considered to be the to be just a random m bit string. Note that at every step of the stream, the adversary also gets to see SIs. What we prove is as follows. Let epsilon be any value between 0 and 1 minus 15 by log n, and p be a t-resilient predicate on k bit input. And we prove that for natural range of values of t and k, that in the streaming model, Goldreich's local pseudorandom generator is secure against all adversaries with at most n to the epsilon bits of memory, as long as the stretch m is less than or equal to n to the order t times 1 minus epsilon. In fact, this result comes under a broader framework. We prove memory sample trade-offs for distinguishing between certain pairs of distributions from samples that arrive in a streaming setting. In general, all our results have the flavor of distinguishing between uniform and pseudorandom distributions. Informally, in our model, memory-bounded algorithms see m independent samples from one of the distributions in a stream and needs to guess the distribution used to generate those samples. We prove a couple of results in this area of memory sample trade-offs for distinguishing distributions. In our first result, we consider the problem of distinguishing between uniform distribution over 0, 1 to the n versus a uniform distribution over a k-dimensional subspace of 0, 1 to the n. Formally, in this, the pseudorandom distribution or a pseudorandom subspace source of dimension k chooses a random k-dimensional linear subspace S and draws samples uniformly, all the samples uniformly from this fixed k-dimensional linear subspace S, whereas a uniform source draws samples uniformly from 0, 1 to the n. And we prove that any algorithm that distinguishes between uniform over 0, 1 to the n and subspace source of dimension k requires either a memory of omega k square or at least exponential number of samples where the exponential is in k. In our second result, we asked to distinguish between a uniform source and a locally pseudorandom source, which are defined as follows. In the pseudorandom source fixes a k-array predicate p and chooses a uniformly random x from n-bit strings, and it generates samples of the form S, B, where S is chosen uniformly from n to the k and B is the output of p on the projection of x onto S. Note that here n to the k represents the set of all k ordered k tuples with exactly k elements from 1 to n. Whereas the uniform source generates samples of the form S, B, where S is again a randomly chosen ordered k tuple from 1 to n, but B here now is also a randomly chosen bit from 0, 1. And we prove that any algorithm that distinguishes between this uniform source and a local pseudorandom source when the predicate p is t-resilient requires either a memory of n to the epsilon or at least n to the order t times 1 minus epsilon samples. This result exactly establishes the security of Goldreich's local pseudorandom generator against memory-bounded adversaries in the streaming model. I want to mention two motivations for our results. The first motivation comes from the area of bounded storage cryptography. This result adds to this area that constructs cryptographic protocols that are secure against memory-bounded adversaries. Secondly, an interesting application comes from the area of average case complexity. In we sh- this this result shows that refuting random CSPs with the resilient predicate is hard for memory bounded algorithms. We have already seen a glimpse of the related work in the area of bounded storage cryptography, Goldreich's PRG, and average case complexity. There's another recent line of work proving memory sample trade-offs for a large class of learning problems, uh, and we in this paper we build on the techniques used in this line of work. We note that there hasn't been much work on proving limitations of memory bounded distinguishers, and this paper might be the first step in that direction. I also wanted to mention another recent work that studies the related problem of distribution testing under communication and memory constraints. Now let's start proving our results. We mentioned before that the techniques used in our paper are inspired from this recent line of work to prove memory sample lower bounds for learning, and we take a brief detour to study one such memory sample lower bound. We consider the problem of parity learning. A secret X is chosen uniformly at random from the n-bit strings, and it is unknown to the learner. A learner tries to learn X from a stream of samples of the form a comma b, where a is another randomly chosen n-bit string and b is the inner product of a with the unknown secret X mod 2. In other words, learner gets random linear equations in x1 to xn in field 2 one by one, and it needs to solve for them. In 2016, Ran proved a breakthrough result showing that any algorithm for parity learning of size n requires either n square memory bits or an exponential number of samples, n square by 25 memory bits or an exponential number of samples. We use this result to prove our memory sample trade-off for distinguishing between a uniform distribution over 0, 1 to n and a uniform distribution over a k-dimensional subspace. Knowing this, let's dig deeper into our proofs. First, we focus on our on problem 1 of our distinguishing distributions, where we want to distinguish between uniform distribution over 0, 1 to the n and a uniform distribution over k-dimensional linear subspace S. So again, a pseudorandom subspace source or dimension k chooses a random k-dimensional linear subspace and draws samples uniformly from S, whereas a uniform source draws samples uniformly from 0, 1 to the n. We prove the memory sample lower bounds for this distinguishing problem by constructing a parity learner using a distinguisher that distinguishes between n-1 dimensional subspace and uniform distribution, and then show that if a parity learner is not possible, then such a distinguisher is not possible. And finally, using a hybrid argument, we show memory sample lower bounds for distinguishing between k-dimensional subspaces and uniform distribution. We use the following simple reduction to construct the parity learner using a memory bounded distinguisher, and hence proving the same memory sample lower bounds for the distinguishing problem. Given a distinguisher for distinguishing n-1 dimensional subspaces and the uniform distribution over 0, 1 to the n, a parity learner does as follows. It guesses the first bit of x, that is x1, and let g be the guess. Note that at every time step, it sees samples of the form a comma b, where a is an n-bit string and b is summation I ai xi mod 2. Now, if g is x1, then the samples a2, a3 to an and b plus ga1, where the last coordinate is b plus ga1, this kind of samples form a n-1 dimensional subspace. It is because it's because there exists x2 to xn such that b plus ga1 is b plus x1 a1 is linearly dependent on the first n minus 1 coordinates. Now if g is not equal to x1, then the samples a2 to an and b plus g a1 as the last coordinate span the uniform distribution over 0 1 to the n. This is because a1 is uniformly chosen is uniformly random from 0 comma 1. A1 is a random is a uniformly random bit. So this means that we can use the distinguishers to see if our guess for x1 is correct or not, and if the distinguisher guesses it to be an n minus 1 dimensional subspace, then you put x1 is equal to g, and if it guesses it to be an n dimensional subspace, you put x1 is equal to 1 minus g, and you repeat it for other coordinates to figure out x. This gives you a parity learner as long as you have a distinguisher between n minus 1 dimensional subspace and an n dimensional subspace, which is 0 1 to the n. And this is all we would say about this reduction. Now let's move on to the second result, whose proof is more involved than Recall the problem. A pseudorandom source fixes a predicate p which takes in k bits to 0 1, and a pseudorandom source chooses a uniformly random n bit string x and generates samples s comma b where of the form s comma b, where s is chosen uniformly from is from n to the k. That's s is a uniformly random a k sized subset of n, and b is the output of p on projection of x onto this subset S. Whereas the uniform source generates samples of the form x comma b, where S is again a randomly chosen subset of n of size k, and b is but b is also uniformly random in 0 comma 1. What we show for these distributions is that it is hard to distinguish between the pseudorandom local source and a uniform source for for memory bounded distinguishers. Now let's see why it is hard to distinguish with low memory and few samples. Note that a pseudorandom source picks x to be uniformly at random from 0 1 to the n, and this is the seed for the m samples where m is much greater than n. As p is t-resilient where t is greater than 0, know that the output of p on the projection of x onto a subset S is uniform over 0 1 when x is drawn uniformly at random from 0 1 to the n. That means that it has the output of p has the same distribution as a random bit b. Therefore, to distinguish between uniform source and pseudorandom source, a distinguisher must try to learn something about x. First, we observe that as it is done by previous papers, that with high probability a low memory algorithm with memory less than n to the epsilon reaches memory states V such that the distribution of x conditioned on reaching these memory states this memory state has high min entropy. That is, it is hard to determine the seed to the pseudorandom source. Then we show that for high min entropy distributions Px given B and predicates P which are t-resilient, for such Px given B and P with high probability over S, which is a randomly chosen subset of n 1 to n of size k, the following is true. That is, if you take the expectation of the output of P on the projection of x over the subset of over this subset S, where x is drawn from this high mean entropy distribution P x given V, then this expectation behaves almost like as it would behave in a uniform source, that is, it is close to 1. Hence, this implies that for most samples S, that the next bit in the pseudorandom source and the uniform source has similar distributions, and hence it is hard for the distinguisher to distinguish between these two cases. And this almost quantifying this almost dictates the sample complexity required for distinguishing under memory constraints, which we show to be n to the order t times 1 minus epsilon when the memory of the distinguisher is bounded by n to the epsilon. And this is all I have for today. Thanks for tuning in.